Welcome back. In the second part of this lecture, we'll be talking about exponential decay and also logistic functions. To begin with, exponential decay is another kind of exponential model, but instead of having a population that's increasing forever, we have a population that's decreasing in size forever. This is still an exponential equation. It just happens to be an exponential function where the power is something negative. So it's the same formula, really. We have the same exponential growth formula that we had before, the same initial amount, the same time t. The only difference is that instead of having a growth constant k, we have a decay constant. And that's because our value for k here will be something negative. So we'll have a value for our decay constant being negative, and the more negative it is, the larger of a negative number it is, that would be the faster our population will shrink over time. The usual application for uninhibited decay or exponential decay would be for radioactive substances. So if you're thinking about any radioactive substance, plutonium, uranium, they all decay over time. And they all follow the law of uninhibited decay. The thing that controls how fast or how slow they're decaying, the way that we measure that is by talking about the half-life of these substances. So when we were talking about things growing, when we had bacteria growing, we might have talked about how long does it take for them to double in size, the doubling time or the tripling time. But for things that are decaying, we're interested in how long does it take for us to have half the original amount. And that's what the half-life measures. When I say a substance has a half-life of 100 years, that means after 100 years, I will have half of the original amount. This gets used when we're estimating the age of artifacts. This is sort of a good application of uninhibited exponential decay. If we're looking at some sort of organic material, a bone or a tree or some sort of plant material that we've dug out of the ground, we can use the fact that every living being has some radioactive carbon in us. And if we know the decay constant for radioactive carbon, we can use that to estimate how old is this bone, how old is this decaying tree, how old is this artifact that we're looking at. But we'll talk a little bit about that when we get to an example with carbon dating. So first, let's just talk about some decaying chemicals. We've got mercury 194, and that chemical has a half-life of 444 years. So every 444 years, half of those mercury atoms would have decayed and become a different chemical. It would have become a different substance. And so the question that we have is, we start out with 300 grams of mercury 194. We're going to just place it on a dish and let it do its thing. And then we want to know that if we were to come back 5 years later, how much of what's in the dish would be mercury 194. So I'll first start off with the fact that we have our initial amount being 300. And we also know that the half-life is 444 years. So what that means for us is that when time is 444, we'll have half of the initial amount. In this case, 150 grams. So if we were to time travel to 444 years in the future and look at our dish, there would be only 150 grams of mercury 194 on the dish. That the remaining chemicals that are on the dish now are the things that mercury 194 has decomposed into. So we're going to use that to come up with our decay constant. We know the amount at time t is our initial amount, e to the kt. And we also know that we'll have 150 grams when time is 444. And so I can solve for my growth constant k by first isolating my exponential function, divide both sides by 300. And then rewrite as a natural log. And I can solve for k. K should be natural log of a half divided by 444. I'm just going to talk here for a minute before we finish the problem, and this is about the decay constant itself. Remember that decay constants are supposed to be negative, and so if you're looking at this, you might be worried because this might not look like a negative number, but we need to remember that for any log function, that the x-intercept is the point 1, 0. And so if what's going inside of your log is something between 0 and 1, then the output would be something negative. And that's what we have here. Natural log of a half, that's a number that's between 0 and 1 going into a log. That natural log of a half should be something negative, which means k should be some negative number divided by 444, which, again, that's a negative number. So, although this might not look like a negative number to you, it is indeed a negative value. So we can now say that a of t should be our initial amount, e to the natural log of a half over 444 times t. All right, so what we want to know now is how much will remain after 5 years, and so we just need to now find out what is a of 5. So putting in 5 for t, and we can solve and find out what the amount is. And in this case, a of 5 turns out to be about 297.7. So there will be 297.7 grams. There's about 2 things that I want to say about this. One is just notation, and one is about how I can actually do this evaluating. So one bit about notation, and I'm going to write this at the bottom. You'll see this showing up sometimes in textbooks when we have e to some power, and that power is not just a single number, but kind of an unpleasant expression that's kind of large. You may see some books writing it, rather than e to the power of, writing it as exp, and then in brackets what the power would be. And sometimes books will do this simply because if you have a power that's got lots of complicated things inside of it, it becomes difficult to read. And so you will sometimes see books writing e to the power of like this, exp, and then in brackets what the power is. So just be aware that that is one way that you could write an exponential function, and it is something that you will see. The other thing that I wanted to mention here was about the evaluating. You could put this through the calculator as is, 300 times e to a power, but you could do a little bit of simplifying first if you wanted to. So the natural log of a half divided by 444 times 5, I could really think of the divided by 444 and times 5 as the fraction, 5 over 444, and it's being multiplied by that natural log of a half. Then using what I know for my log properties, that 5 over 444 could come in front. and come on top as a, come from on front and be now a power on that half. So I would have e to the power of natural log of half to the power of 5 over 444. And the e and the natural log would undo each other. I'd be left with 300 times 1 half to the power of 5 over 444. And so one thing that you can do just to confirm that the answer that you get with this expression is actually the same as the answer that you get with this expression. That the decaying mercury could be expressed, we had it originally expressed as an exponential formula in terms of base E, but it could be, using our log properties, rewritten as an exponential function with base 1/2. All right, so one last question to answer here, which would be for this mercury, how long will it take for only 10% of the original amount to remain? We started with 300 grams, and so 10% of the original amount would be 30 grams. So what we want to know is, when do we have 30 grams remaining? So we have, as usual, our exponential decay formula. A of t is our initial amount, e to the k times t. And I know that I want 30 grams in the future. And then I'm just going to solve for t. Dividing both sides by 300 gives me 1/10 on the left side. Rewriting this as a logarithmic equation. So log base e, natural log, switching the inputs and the outputs. And then solving for t. And so we have that t should be 444 times natural log of 1/10 divided by natural log of 1/2, or about 1,474.936. So it'll take approximately 1,474.9 years. One thing that we should maybe just think about here is whether this answer even makes sense. And it does, if you're thinking about the fact that our population, in this case the amount of mercury, will go in half every 444 years. So after 444 years, you'll have 150 grams. And then 444 years later, you'd have half of that amount, which is 75. And then 444 years later, you'd have half of that amount, 37.5. And you can see that already at this point, we're at 1,300, and we're at over 1,300 years. And that's to get us to 37 grams. To get down to 30 years is going to take a little bit longer, and not a surprise, it takes us all the way up to 1,474.9 years. So this does seem like a reasonable answer then. And now let's look at an example involving carbon dating. Just to give you the idea of how carbon dating works and why it works. For all the carbon that's on the planet, all of the organic material that's on the planet that contains carbon, there's a certain percentage of that carbon which is radioactive, and that's known as carbon-14. And it's got that half-life of 5,730 years. When you're alive, the amount of carbon-14 in you is pretty much a constant proportion. And that's because the radioactive carbon gets inside of you from you eating other things that were once alive, plants and animals. The only time you start losing the radioactive carbon that's inside of you is when you stop taking in new carbon. So once you die, and once you stop taking in food that has radioactive carbon inside of you, then the carbon that's inside of you that's radioactive will be decaying and you won't be replacing it. And this is how carbon dating works. We know roughly how much of your carbon should be carbon-14 if you're currently alive. And so when we find a fossil, when we find an old tree, when we find a bone, we can compare how much carbon-14 is currently inside of it versus how much would be inside of it if that person were alive today. And we can use the known half-life of carbon-14 to estimate when did that person stop taking in new radioactive carbon? When did that person or that animal or that plant, when did it die? And that's how carbon-14 dating will work. Now, before we can get to that, we need to find our decay constant. And so this is where we'll start off with our usual formula, that AT is the initial amount times e to the kt. And we know that the decaying for carbon-14 has a half-life of 5,730 years. So when time is 5,730, we should have half of the initial amount. So the fact that I don't know what the initial amount is not a problem, because I'll divide by whatever that initial amount is, and I'll have an equation just in terms of k. And then I can use this to solve for what k is by rewriting this as a logarithmic equation, switching my inputs and my outputs. And then dividing by k, I get my decay constant, natural log of a half, divided by 5,730. So there we go. We've got our decay constant. And now that we do, we can use that to find out how old this animal bone is. This researcher has found a bone in the cave, and we want to be able to estimate when did the animal die, how old was that bone. And so what we know is this bone still has 83% of the original carbon-14 amount. So in other words, what we know is the amount that we have right now is 83% of the original amount. And we want to know what is T. So using our formula, we know A of T is A0 e to the growth constant or decay constant, in this case decay, natural log of a half over 5,730 times T. And we know that the amount that we have is 0.83 times our initial amount. And then I'll divide both sides by our initial amount, A0, and that gives me 0.83 is e to the power of natural log of a half over 5,730 times T. And now we're just solving for T, as always, rewriting this as a logarithmic equation, switching my inputs and my outputs. And then I find that T is 5,730 times natural log of 0.83 divided by natural log of a half. And then I can solve for what time is here by running this through my calculator and finding that it's about 1,540.3. So the animal died 1,540.3 years ago. And that answer again seems reasonable because since we have almost all of our original carbon-14, 83% of it, we couldn't have passed the half-life of 5,730 years. If we were past that, we would have half the original amount at that point. Since we have more than half the original amount, it's been less than the half-life. It's been less than those 5,730 years. So 1,540.3, that seems at least reasonable, and there we go. The last type of model that we'll look at fixes one of the problems with exponential growth, which is that for exponential growth, there was no upper limit. If you're imagining the bacteria in the jar, the population was going to go up forever, that there was no maximum size for the population of bacteria in the dish or whatever the substance is that we're looking at. And that's not totally realistic because, of course, even for bacteria in a dish, there are limits to how big the population can grow. It's limited by the space that they're in, it's limited by the amount of food that's available. There are all sorts of things that will slow down population growth. And so another kind of a model that involves exponential growth but with limits on how big the population can be, that model is a logistic model. So here the formula for a logistic model is this. It is something that involves an exponential term. A of t is equal to c over 1 plus a to the e to the power of negative bt. And here we've got a couple of things. Number one, we have that the numerator for this fraction, that represents the maximum population size. That's the so-called carrying capacity. So in the example that I have here, I have a of t is equal to 5 over 1 plus 4 e to the negative t. And so as time goes on, we'll reach the maximum population size, or we'll get close to the maximum population size of 5, but we won't go past it. So our population will increase for a while, but after a while, after we get about halfway to that maximum population size, we're starting to run out of room, and so our population will grow slower and slower and slower, tapering off to that maximum population size. For this formula also, you have that the y-intercept, that's the value that happens when t is 0. If t is 0, you would have e to the power of 0, which is equal to 1. So if t were 0, you would just be left with c over 1 plus a. Or in other words, the y-intercept is c over 1 plus a. All right, so here we've got an example of a logistic equation. And if we're looking at a of t, this is representing the number of trout that we have in our pond. So we initially stock a certain number of trout in the pond when time is 0, and then after a while our population will grow and there'll be some sort of maximum population size. So first off, the initial population size, that's the y-intercept, that's what's our population when time is 0. And if we put in 0 for t, e to the power of 0 would be 1. So we would have 18,240 over 320, which turns out to be exactly 57. So initially, there are 57 trout. And then part B, what's the maximum size for this population of trout? Or in other words, what's the carrying capacity? And that's just the numerator. So our population of trout will never get larger than 18,240. How many trout will there be in the pond after 3 years? So this is the population size when time is 3. And so that's just a matter of putting in 3 for time. So the power is e to the power of negative 0.8 times t. And that's negative 2.4 for that power. And when I ran this through my calculator, I got about 609.2. So in 3 years, there will be 609 trout. All right, and there's one last question that I want. So we know the maximum population size is 18,240. And we might want to know then, well, since we're going to have a maximum size of 18,240, then at some point the population must reach 10,000. So when is A of t equal to 10,000? So we'll put in 10,000 for A of t. And now it's just a matter of us solving for t. So the first thing I'm going to do is I'm going to take that denominator and bring that up to the left side. So I'll have 10,000 times 1 plus 319 e to the negative 0.8t equal to 18,240. And then next I'm going to just expand what I have on the left side. I'll multiply that out. And now I'm going to do the same thing that I usually do. I'm going to eventually isolate that exponential expression. So first, subtracting 10,000 from both sides. That leaves me with 8,240. I'll divide both sides by that 3,190,000. And then I'll rewrite this as a logarithmic equation. And once I've rewritten it as a logarithmic equation, then all I really have to do now is just solve by dividing both sides by that negative 0.8. And there we go. I'll have what t is. And when I run this through my calculator, I got approximately 7.448. So about 7.4. So in 7.4 years, there will be 10,000 trout. And there we go.